In the second question first, we say a stochastic process is called wide sense. Stationary process. If it satisfies that its mean is a constant and its autocorrelation is a function of time difference. And then we say that this process is a wide stationary process. And second, independent increment process. And this means that for a process xt1 minus xt2 and xt3 minus xt4, and if they are on non-overlapping time intervals, are independent. And then we say this is independent increment process. And third, we say a process xt is a Markov process, and if the past has no influence on the future, which means the future is only relevant to the present. And when the present is known, we see that this process is a Poisson process, and we can use the probability to represent this xn equals to xn minus 1 equals to xn minus 1, and n2 x0 equals x0, and this the probability equals to xn equals to xn under the condition xn minus 1 equals to xn minus 1, and this is the Markov process. 4. Normal process. And a process xt is said to be a normal, and if it satisfies this condition, if the random variables xt1, xt2, and into xtn are jointly normal for any n and any t1, t2 until tn. And that is, we can write its probability density function f x, x1, x2 until xn, t1, t2 until tn. It equals to 1 divided by the square root of 2 pi to the power of n, and the determinant of c multiple e to the power of 1 divided by 2 multiple x minus eta t, the inverse of c and x minus eta. And x eta, they all matrix, and c, they all matrix. And the x equals to x1 until xn, and x equals to xt1 and until xtn, and eta equals to the expectation of x, and the matrix C equals to the expectation of x minus eta and multiple x minus eta t. Five. We see a process to be a strict stationary process, and if it satisfies that it is statistics, is not influenced by time shift. On the time axis, and which we can use the probability density function to express this x1, x2, and until xn, t1, t2, and until tn, it equals to fx, x1, x2, and until xn, t1 plus epsilon, t2 plus epsilon, and until tn plus epsilon. And this is the strict stationary process. In sixth, white noise. And for a linear process, Wt, and we want to talk about its derivative, and we let Vt equals to the derivative of dWt, and because the expectation of Wt it equals to 0, and we can know that the expectation of Vt it also equals to 0, and the RV T1, T2, it equals to alpha multiple delta. Delta is impulse function T1 minus T2. And we see a process Vt when it satisfies that the expectation of T it equals to 0, and its autocorrelation function RVT1, T2 equals to Q T1 multiple delta T1 minus T2, and we see that this process is a white noise. 7. And a stochastic process xt is said to be a mean ergodic process if it satisfies that the limit when t approaches to infinite, 1 divided by 2t integrate from negative t to t, xt dt, it equals to the expectation of xt. And if it satisfies this condition with in mean square signs, when it satisfies limit when t approaches to infinite 1 divided by 2t, and multiple the integrate from negative t to t and xt dt. Xt dt equals to the expectation of xt in mean square signs. And if it satisfies this condition, we see that this process is mean ergodic process. And for 8, a stochastic process xt is said to be a martingale if it satisfies that its expectation xt under the condition xs equals to x1 equals to x1, and when where s smaller or equals to t, and if xt if a process xt it satisfies this condition, we see that this is martingale. And so this is the second question.